Okay, so that is better now. Good morning, everybody. I'll just go from beginning. Okay, so today we'll start with a little programming exercise that is based on Lewis Carroll's pillow problem. So let's start it. And then I go this. And the link to this worksheet is here. So I'll post it in the Slam channel. So I'll give you an introduction to the problem, and then you should try and implement a solution to try and answer the question. Now, Charles Dobson is better known by his pen name, Lewis Carroll. And what is he famous for? He was a writer in the 19th century, lived from 1832 to 1898, and his most famous book is Alice in the Wonderland. Yes. Which is world well-known fairy tale, children's story. But it's actually very clever. If you read it as an adult, there's a lot of subtlety in it. It's a very interesting book. He was also an accomplished amateur mathematician, his specialty is in the area of recreational mathematics. So if you, he's sort of similar to Martin Gardner in that respect, who is a 20th century recreational mathematician. Um, he is famous for his columns on in Scientific American. Oh, wait, Mathematical Games was the name of this column. So he wrote the book Tangled Tale, where he included some problems that he said he liked to work on and solve just before he went to sleep, which meant while he's lying on the pillow. Right? That's why they're called pillow problems. The interesting thing about that is that I tried a lot of those, and actually, even with pen and paper, they're not easy. So if you can solve them in your head, lying in bed, then the more power to you. That's quite an achievement, I think. So let's have a look at this particular puzzle, which is one of my favorites. And it sort of shows that that probabilities can be quite subtle and tricky, so you have to be careful when you deal with them. So the problem is as follows. A bag contains one marker, one counter, call it, known to be either white or black. A white counter is added to the bag. I just want to copy the text. Bag is shaken, and the counter is drawn out. What is now the chance? Drawing a white counter. So this is the problem. So think about this for a second, and then see how you can work that out in your head. So I have a bag, I have two markers, white and black. One of the markers, without looking at it, is put in. So there's a 50% chance that that marker is black, and a 50% chance that the marker is white. Right? Then you add another white marker. So now you have two markers in the bag. You shake it, you pull one out. That one is white. If you now put your hand in the bag again, what's the probability that you will get another white marker? So if you're very clever, I guess like Lewis Carroll, then you can work that out in your head. If you're not so clever like me, you can at least write a computer program to simulate this and then work out the probability. Write a simulation.
I prefer my head.
Not in this class. You can use your head. Lewis Carroll did the same way. So he published a proof. And he said, of course, the probability must be 1/2, right? Because we'll get to that. The situation, Lewis Carroll's proof, after drawing the white marker, is the same as prior to adding the marker. So if the probability was 50% before, and you put in a white one and you pull out a white one, then the probability shouldn't change, right? So before adding the white marker, the probability is 1/2. Then we add a white marker and take out the white marker. So the situation is the same. So that proves that the probability after must also be 1/2. So now for the next 15 minutes, implement a simulation and confirm that 1/2 is the correct probability. So run 1,000 experiments. Actually, you can work that out for yourself, how you want to implement the simulation. But you want to follow exactly the instructions that were given. So create a bag, put in a marker with 50% or later on p% probability is white and 1 minus p is black. And then draw a marker If it's white, then continue. If it's not white, then start again from scratch. And then pull out another marker and then check what the probability is that that marker, the second marker that you draw, will be white. And then you can confirm Lewis Carroll's results. And you want to plot them. So make a chart using Matplotlib that shows the probability. Count how often do you get a black one, how often do you get a white one.
So the x-axis will be the present time.
Hmm?
What the axis of x represents the unit.
That depends on what you want to draw. What x can be the number of the experiment, right? And then you can plot. 1 is white, 0 is black, and then you get that kind of a curve. Something like that, right? That would give you an idea. That's not bad to plot, just to make sure that your experiment is running correctly. But really, in the end, all you want is you can just do a bar chart with shows. I ran it 1,000 times, 500 red, 500 black, 500 white. So you just need to show the sum at the end. But you can plot also those to get some more experience with how to plot data in Python Matplotlib. So take that opportunity to improve your programming.
Yeah. Isn't there any function can have a particular value from the list in Python?
Take a particular element from the list.
Yeah. In value, but not in complete detail.
Remove.
Remove all.
If you want to take something out of a list based on value, then you can do remove, and it will remove that within the list. Otherwise, I think will. I'm not sure if it returns -1 or if it throws an exception. But you can do help list.remove and it will tell you.
In your ID.
Yep. Like here, if you're not sure, one nice thing about Python is that it has very powerful help functionality. So you can just go list.remove. Remove first occurrence of value, raises value error if the value is not present.
Oh.
And since we talk about programming and um, software design, so here, if I have a list, with 1, 2, 3, and then I call, then I print the list, then I call list.remove 2, then I can remove the 2 from the list, right? Which is what you would expect. Then now if I call list remove 4, then I get a exception, right? Value error.
Yeah.
So what's the correct way of dealing with this?
Use the exception function.
Yeah, that is actually the correct way. A lot of people would implement something like this, the safe remove, for example. And then remove X from that list. And then they write something like this. If X in list dot remove X, else. So now I can call print C, say remove 4 from the list, set the list to 1, 2, 3 again. So then that's okay, right? It will return true. It should return false. Right? Now I don't throw an exception because I check if X is actually in the list. So this should succeed here. Right? This should not cause an exception. However, this is what's considered an anti-pattern. In modern software design. So a pattern is a snippet of code, like a small piece of code or it could be a large piece of code that is often used in various programming languages. We use the same thing to solve various problems. So what kind of patterns do you know?
Factory.
Yep, a factory pattern would be one. And what does a factory pattern do?
Uh, Actually, I never tried. I remember. I remember the story of the pizza store and
Of the what?
the pizza store.
Pizza store.
Yeah, yeah. In a factory, the pizza store will customize the customer's pizza. So every function is not so intact, and you make a lot of incomplete function to building a whole program.
Right, that would be an abstract factory, yes. For factory, that one is a little bit easier to understand. For factory, you just pass in some arguments to create a sub-object, subtype of some class. So for example, if you have if you have a type hierarchy where you have animal, dog, cat, bird, and then you have different birds, parrot or pigeon, right? Then often it's convenient to have a function that has a bunch of parameters in particular type as a string and says, okay, now I want you to build a pigeon, and now I want you to build a dog, and now I want to build a cat. And then returns that object of the correct subtype. Okay. So in user interface design, that also happens quite often where you have a text description, let's say you have a text description of your user interface, and you want to have run it on mobile and on desktop PC. So on different operating systems. So you may have in your own code, you may have something like a selector. And selector can choose any numerical value. So you may implement that as a combo box or a text edit box or a number of buttons that the user can click on, right? Depending on what kind of operating system you have and what user interface types is supported by that operating system. So then you pass it into a factory function which will return the best type it can for the constraints that you have. Okay? So that's what a factory would be. An abstract factory is one where all the functions to build things are abstract functions, so that you need to specialize them to make a pepperoni pizza or a Hawaiian pizza or something like that. That's a common pattern. Other ones that are and there's a whole book of them. It's a famous book by the group of four that has a whole list of these patterns. Singleton. So a singleton is something where you just want to create one, but you want to use it throughout your code. So for example, if you have an application, you write a program, a large program, and it uses a database, right? Then the database, you want to abstract that away from like accessing various tables or the data in the database, right? You want this to be its own class, but you want to make sure that there's only one database connection because you need to be able to lock and unlock the database. You cannot run two updates at the same time, for example. So in that case, you would implement a singleton object where basically it's set to null. The first time you call it, it creates the database object. The next time you call it, it doesn't create a new database object, it just returns the one that it previously created. So this is also very useful in lots of programming. Model view architectures are also patterns, observer patterns. In order to pass data through your application, instead of having to check every time where data was changed, you can have an observer class which just watches, for example, you're designing an app in order to do shopping, right? Then if they add one more bag of rice, the price has to be recalculated. But also the shipping box has to be changed. So you can have, instead of having to say, oh, now I changed the price, now I have to call update shipping and I have to call update price, you could have an observer pattern where this class says, oh, I need to know if you changed this, then I need to update myself. So that's also a very common pattern. So what's an anti-pattern then? for caching of intermediate variables at your application level, that would also be a pattern. So an anti-pattern is
you write a redundant code.
a snippet of code that is common, that is used often, but it's wrong. And it's not uh, it's not wrong in the sense that it's not working. It's wrong in the sense that it doesn't give you the guarantee that you hope you actually have. It doesn't work that you think it should work, right? So anti-pattern is something that you don't want to use. It's a bad thing. You don't want to implement anti-patterns, and safe remove would be one of them. And this is what's meant by also by duck typing in Python in general, but it also applies to any other kind of programming. So what's wrong with safe remove? Why is that a bad function?
Because safe remove is a function for a local application. So
No.
it cannot be used in anywhere other than this way.
No, that's not the problem. In fact, it would be very useful, right? If it were a pattern, then it would be nice to move it everywhere, and then I could just use the return value. I could just check. If it's true, then something was removed. If it's false, nothing was removed, and there was an error. So that seems pretty nice, right? But the problem is, what do you want it to do? What do you want to avoid by having safe remove? Why do you implement safe remove?
Because we want to avoid the exception.
Correct. I want to make sure I don't get an exception. So the But the problem is, this is not guaranteed. Why not? Let me make sure I can actually do this. Okay, so I have to. Oh, wait, I can just do that. Yeah, let's see if that works. No. So how come this is okay, so try and draw your charts and I'll work on my frame here. Just make sure I doesn't. Wait, it only runs the first version that I have. Oh, And the problem is those threads are still running, and in the current environment, yeah, because the collaboratory,
Yeah, I'll just restart. You are sharing the same computer with other users.
no, I think that actually is not a problem right now. Um, but yes, I am sharing it with other users. But I think the problem is just the thread started and made a mistake, and now it keeps running because there's no way to really kill a thread um, in Python. Or in most programming languages, killing a thread is not a good idea because if that particular thread holds a lock to the database or anything else, then you won't be able to access it. So usually you don't want to have a thread you can just kill. Okay. Okay, now that's what it's supposed to do. So now it'll run 10 times and then it should cancel and we should terminate it. And now it completed. So why? Oh, it's not done. So here, while not done. So now I have my thread. And once it's 11, this will be true. Then so then we set the done flag to true. Then this while loop will terminate, and then we can wait for the thread to finish. So that we have set up now. And now,
So what's the my run function for?
that's just what this is just starting a thread that right now just counts up from in 1 second interval. It counts from 1 to 11, right?
Yeah.
Which is not that exciting at the moment. We, however, want to show how we can generate a problem here. So let's make the list a little bit bigger. And now, instead of doing this here, so I want to remove element 1. from the list. So far, so good. Oh. So after we remove, and I can also print it before remove. So far so good, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I remove the 1, I end up with 0, 2, 3, 4, 5, 6, 7, 8, 9. Right? So the 1 is gone. But now, you put some more print statements in. So this is in the list. So here we can safely remove it. That's what we think. So 1 is in that list. Then after the sleep, we still have the list. So I can remove 2. So what do I have to change now to make it crash, or to try and make it crash?
Oh, just adding adding more count.
Any more count? No. No, not quite yet. Right now, my run doesn't actually touch the list, right? But I can do this, right? And then I guess we just go up to run. And, And now, bam, now my program crashes, right? And it crashes because list remove fails. And that's because after my sleep, the list now is empty, right? So here I have a function and I put in the sleep commands just so that I can trigger the bug, the error, in the first run. If I take the sleep commands out, then there's a certain probability that it will crash. There's another probability that it will succeed, right? But if you do this in your database server or in your web server, where you run several millions of transactions per minute, then that bug is definitely going to trigger. You can guarantee it. Right? So here we now have a race condition because we have two parts of the program that will access the list. The one part is in save remove, right? The second part is in my run. And actually I can make it not a global variable. If you don't like that, then
if only have the one thread, why why there are two functions which
because I start one new thread, but I also have my main thread which is always running. Right? So if I start one thread, then I actually have two things going on at the same time. And lists in Python are passed by reference, which means I only get a pointer to that list. So when I call the function, it doesn't actually make a copy of that list. Right? It just has a pointer to memory. If another thread changes the list, then the value in your main thread will also be changed. Right? It's a normal pass by reference. So this is why that particular save remove is an anti-pattern, because in a modern application, right, you are guaranteed to run multiple threads. Very likely that you will run multiple threads in anything but a non-trivial application. Why do we need multiple threads?
because we want to utilize our hardware.
Right. In order to write an efficient program on a modern CPU, you have to use the parallelism. You have to make use of the fact that you have a superscalar architecture with 4 cores or 8 cores, or 12 cores, or how many cores you have. Right? So to keep the CPU running, you need to have lots and lots of different instructions that the CPU can basically execute, because it's extremely fast. Anytime you request something from main memory, right? The CPU basically goes on vacation for a week. And then, oh, okay, here's the data. Okay, now I can do X plus Y. So if you want to keep the CPU running, you must have multiple threads for efficiency purposes. That's almost given nowadays. So if you have an application like computer vision, you want to do some fancy network with some robot inverse kinematics calculations, things like that, then these all want to run in separate threads. Also, any kind of application that has a user interface guaranteed will use multiple threads. At least there will be one thread for the user interface, another thread to actually run the application. Because you want to be able to update the buttons and the widgets and the animations, right? While your application is executing. So if you implement something in Windows with Windows and buttons, or in Linux or Mac OS, definitely you'll be running multiple threads. So nowadays, in 1980s, very few people actually wrote multi-processor systems or multi-threaded applications. So there, the safe remove was a good idea, right? Because if you only have a single thread, then this will work. But nowadays, in um, in the kind of applications that we write nowadays, you have to expect that you run with multiple threads. If you run with multiple threads, then safe remove doesn't make sense. Because even if you check, right, even if you check that it's in the list, it doesn't mean it's still in the list when you actually call remove. So the correct pattern for remove would be, which is what all that duck typing is about, in Python as well. Oh, this is the, so if that is important, then you access the list, by the way, or then of course you can use mutances or semaphores or other locking mechanisms, but then you slow down the program a lot. So the Pythonic way is to try and execute remove and then catch the exception when it fails, if it fails. Because even if there's just a microsecond or a nanosecond between checking if it's in the list and then calling remove, there's a chance that another thread will jump in exactly at that point and will overwrite the data. usually the full locking means that you basically give up all advantages of running things in parallel. Right? If you have a mutex, then only one thread can access the critical section, critical region. So that's a huge overhead that you have to pay. So we try and apply this dot remove 5, and then we catch the value error if it occurs. Right? And then my program will not crash. I can continue to execute things. However, since I have to be ready to catch the exception anyway, there's no point to check first if it's in the list or not. It's completely wasted, which is why that particular save delete function would be considered an anti-pattern. It's not something that we want to implement. Okay, but this was just a small excursion, a small detour. So how about my pillow problem? You finish it now? And
And I found that I think uh, yeah, I think the black, yeah, they are staying for good.
no,
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 or what white will be
no, no. It's more than that. So I think the problem is with yeah, your problem is with this particular line.
This one,
Yeah.
the line is the bag is there are only one ball in the bag. Why is
Right.
that incorrect? Because I already cleared for every time.
For the next run. So if you append white, how many bins? 10 bins, 1,000. Should be just two, right? Black and white.
I just found
Yeah. Okay. But okay, not 1,000. Definitely not 1,000. Maybe three. Then you get a white border in the middle. But anyway,
so the answer is wrong.
yes, the answer is wrong.
Oh, so the black will be higher a little bit.
No, not just no.
Not just little bit.
No. Because Lewis Carroll is not just a good mathematician, he's also a little bit evil comedian. So his proof doesn't actually work. It's convincing, right? It seems to make sense, just like lots of things in probability, but it's actually wrong. And the I think your problem is with the remove, um, and then returning always the first element.
Okay. Maybe you can check the
back,
family. Yeah.
but not too many of those.
Yeah.
Yeah, they're white and black.
Yeah.
But that's our usual problem. If you just look at the printout from an individual print statement, then it's hard to see that your program is working correctly or not. But let me try and implement my solution, and then we'll see. Analytically, you can also prove that the answer is not 50-50. The answer is not one down. But the program is good. It's just a subtle. It may even be in the. It may even be in the number generator, random number generator. I need to see about that. So we got your result. Okay, then add them up. What's the probability of getting 0 or not in your plot? And this plot now shows you the result for every trial. But now you want to count any ones, any zeros. So matplotlib, in this case, you could just call sum on A and it'll tell you how many ones you have. You can just count them up. Yeah, 50% white, 50% black. Correct. Yeah. Then you pull black out, then you pull yellow out. It's a white ball, definitely a white ball. So you check that's a white ball. So then the question is what's left in the back? That's what Lewis Carroll said in his proof. Yes, but actually he was joking. That is not the actual value. Yeah, now I'm curious what will happen. I haven't implemented this myself yet. So let's see. So I'll write one function, run the experiment, and I'll give a probability p just so that I can change it afterwards. And I have different bags, so I will count black, white, is 0, 1. So if random dot random is p, let p be the, so with p probability it's white. So if random dot random is less than p, the counter is white, and else the counter is black. So now I have a bag with the counter inside, and I add one white counter, right? So now I pull out of the bag one of them, so 0, 1. So if it's not a white one, then it's not what happened, right? Because I pulled one bag out, and that was a white counter, so if I now pull out a black counter, then that doesn't count. So I return none, and then I return, in the other case, I return back, there's only two of them in there, so that would be 1 minus this, it would be the other one, right? So let's run 5 trials. Now P initially is 0.5. y is not none, then it was successful. So ys in trials is equal to y in trials in trials plus 1. So let's just print them out quickly. I'll get all white. That looks a little bit weird. 2 many whites. Check what's in the bag. Print bag. Index. Zero one. Index 1. 0 1. 0. Okay. Then so we return minus the index from the bag. Bag. Get index. Index. Bag 0 1. We return a 0. So how come I don't have the 0 here?
you probably you forgot to clear your set to empty.
No, here it's created new, so I don't have to clear it. I create a new bag. So that should be okay. And I think it's here somewhere. Ah, what's the problem? Zero. Y zero. So y is one, y is none, y is zero. Yeah. Uh, this is the problem. Zero is the same as false. So I have to say if it's none. I thought y is only if it's none, but zero will also not trigger. So that's obviously the first one. Not if it's not. If it's not none. So now we get 0, 1, 1, 1, 0, 1, 1. Okay. So I can plot that. So this is just a small plot to sort of get a better idea of what the data looks like. And now this is the output. But that's not what the question actually asked us to do, right? We're supposed to calculate what the probability is. So let's, So here's our output. How do I calculate now the probability of getting a white one, a white marker?
Calculate the area of the blue.
Yeah, that's
Equal.
that's what I could be doing. Yes, but it's easier than that, right? Because the only thing I have in my array is zeros or ones, right? So if I want to figure out how many ones I have, I simply have to
Sum of the array and divide by 100.
divide by the length of the array, and then multiply by 100. So let's run another one, and let's just add that. I still want to plot it, but P probability of having a white marker then would be the sum of the y's divided by the length of the y's. And let's see what I get. Uh, I think that's right. So now I have 68%. Right? And what did you get for your probability when you run the experiment? And run it again. So doesn't seem to be 50%. The Lewis Carroll's answer was 50%. I can run it a number of times. Now I get 70%. I can run some more. Instead of 100, I can run 1,000 trials. And then I get 66%. Actually, I think this graph now looks a little bit wrong because of the width of the line. So I think 65%. So what answer do you get?
Same.
Same. You.
Yep. Almost. Oh, maybe more higher on the maybe around the.
Let me see your program. Okay. Yeah. That's not quite right though.
Really?
Yeah. Because you're adding a white one,
Uh-huh.
then you pick one from the bag and then you just check if it's black or white.
Yeah.
But that's not actually what happens, right? You have one marker in the bag,
Uh-huh.
You put another white marker in.
Yep.
You draw one marker. You look at it. It's white.
Yep.
And then you need to know what's the marker in the back still.
Oh. Oh, yeah. I forgot.
And you. Okay. Yeah. Um, yeah. You just need, the approach is correct. You just need to figure out the syntax for it.
I still don't know why my code goes wrong. So, but I find that the written choice is not so good. Yeah.
Oh, wait a minute. Let me have a look.
This is
No, 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 go up.
well,
Okay.
the white will be more preferably choice.
Yes, the white will be the more preferred choice.
Or any kind of
So where you print this, this one is actually correct. That right here. So your bins are correct. You just didn't calculate it correctly.
even though
Alright. And try and write your own code, not just copy mine. So then we can also draw the correct chart that we want. I could I could generate another figure. Two bins. So let's see if that one was correct. In the sequence, the left edge of the first pin and the right edge of the last pin. So I think this needs to be 1 for 1. Yeah. So then this would be the plot that we have. So probability of black is 1/3. Probability of white is 2/3. So why is that? Um, you can draw all the possible outcomes, and then you can also prove it analytically. So initially, we have an empty bag, right? So now we put in one marker. Now with probability 1/2, it's a black marker. With probability 1/2, we have a white marker, right? So now I add another white marker with probability 1. So in this case, I would get black and white. In this case, I would get white 1 and white 2, basically. Right? Two white markers. So now I draw and I get a white marker. And this branch here, where I draw the black marker, that one is discarded. Because I know I got the white marker. Right? But this only happens with probability 1/2. Right? Because I have 2. So with probability 1/2, I draw the black one, but that didn't happen. With probability 1/2, I drew a white one. So now here, I either draw W1 or W2, doesn't matter. That happens with probability 1/2, 1/2. And then here I would draw W2, here I would draw W1. Right? And that would happen with probability 1, because there's only one net in the bed. This point here, I have the black one, I draw this one, so now with probability 1, I would get a black marker. Here, I get a white marker, here I get a white marker. Now the tree of events, like the probability tree, I can calculate what the probability is of each one of these branches. So what's the probability of ending up here?
You 33.
33%. I think I end up with 33%.
There are three possible outcomes. And
Right, yes. If I just look at here, I can immediately tell that it's 33. However, to be to go through it step by step, you would calculate the probability of this outcome here. So this will happen with probability 1/2 multiplied by 1 multiplied by 1/2 multiplied by 1. So probability that we end up here is 1/4. And similarly here, 1/2, 1, 1/2, 1. So this should be 1/4. And the probability that we end up here is 1/2 multiplied by 1 multiplied by 1/2 multiplied by 1, which is 1/4. So here, I get a white marker with 2/4 probability, I get a black marker with 1/4 probability. So that means this one here will occur 66% of the time, this one will occur 33% of the time. However, this is not easy to see, right? And the initial proof by Lewis Carroll that sounded convincing. I put a white one in, I take a white one out, so nothing changed. But in fact, everything changed. Because then the probability went from 1/2 to 2/3. So seemingly small changes in the way that the experiment is set up will lead to completely different results. Here would be the example based on Lewis Carroll. He has another one in his pillow problems where he has a very convincing proof that turns out to be wrong, and he knew that it was wrong. He was just putting it in as a joke to make sure that his readers are paying attention. But this is a very fun problem. I like this one. It's easy to sort of be mixed up. Now we can run some tests. What happens if I put in a white marker with the probability of 1/4 instead of 1/2? Then how will that change the probabilities? Am I more likely to get a white marker then, or less likely to get a white marker?
you mean you adding an extra one.
No, here my initial probability instead of 0.5, I make it 0.25. So now the bag, initially, at the beginning, my bag now has 25% chance that there's a white marker, 75% chance that there's a black marker. Then what will happen to my, then I go through the same process, I add another white one, I pull one out, it's white, What's the probability that the remaining marker is also white?
Of course, we the calculator.
You would hope so. Yes. I think in that case you end up with 50% actually. Because in this case here you would have 3/4, right? 3/4 multiplied by 1 multiplied by 1/2 multiplied by 1, so that would be 3/8, right? Then this would be 1/4 multiplied by 1 multiplied by 1/2, 1, so this will be 1/8. So in this case, you will be more, there will be a 66% chance that you get a black mark. Because this one I said 3/8, right? And this one is 2/8, 1/8 and 1/8. So let's run it. And you can also just put it in a single plot. Okay. Um, So now the black marker has about 2/3, the white marker has a probability of 1/3, which is what we would expect after we look at the result tree here. Three quarters times one half, three eighths. Oh, three eighths versus two eighths. Yeah, it's 40%. Yes, not 66%. Here we have three eighths. Here we have one eighth. One eighth. So 3 plus 1 plus 1 is 5. Right? So this will happen with 60%. This will happen with 40%. If the probability is 0.25%. Right? And the trick or sort of the confusing thing is that I tell you that the white marker was wrong here. So this branch is cut off, right? This doesn't occur. So the whole probability of this particular branch here is sort of not taken into, that's why these numbers don't add up to 1. 1/8 plus 1/8 plus 3/8 is 5/8, not 8/8, not 1. So 3/8 is this branch here, but I tell you conditionally that this didn't happen. What are the remaining probabilities? So like I said, a pretty fun problem. You can change P. You can do some more plotting or drawing with Matplotlib. Uh, Actually, one thing that I would like to do is change the colors, and I think you can change histogram. Change the color. So make it look better. Except I don't want electric white. I want. Hey, let's see. One color per data set. Okay. One data set. Oh, Okay, so that the color CN has to be applied to the different data sets. So I cannot change the color. If I want to do that, then I have to make two plots to histogram. And in that case, I could just make the bar chart. So actually, I have to call histogram itself. So it would probably look better this way. So here we generate the lists, filter them by whites and blacks, and then the length should give us the probability divided by the length, which will give us the probability. And then I want to do a bar chart. Excess, so 0.5, 0.25, 0.75, blacks, whites, width of the bars, 0.8, 0.9, let's try 0 to 1. So yeah, white is not so good. So let's take light gray, which would be maybe 80. So then you can plot it like that. A little bit nicer. So again, extremely powerful visualization library, Matplotlib, lots of different things you can do with it. And especially in applications that involve probabilities, like you saw when you wrote your program, and you had a bug in it, if you just print out white, black, white, it's very hard to see whether this is the right output or not. Very, very difficult. So if you often need to generate some sort of visualization, you need to actually plot the data to make sure that the probabilities that you're expecting are sort of is what is actually happening. And plotting the data, even though right now this particular plot here on the left-hand side doesn't look so useful, this particular plot, this can also be very helpful because if there's some dependency in your data, then this is what you would sort of be able to pick up on, right? So for example, if you draw white and then 3 reds or two blacks, if you draw 1 black and then 2 whites all the time, then the probabilities would come out correctly, right? It would be 66%, but the pattern here would not look random. If it's always 1, 0, 0, 1, 0, 0, 1, 0, 0. That's something that if you print out the numbers and 1,000 of them scroll by, may also not be so easy to pick up. But if you look at a plot like this, then often you can figure out what's wrong, that there's some dependency. So, for a lot of things nowadays in science and machine learning, if your gradients are working or not, these kind of visualizations are essential in order to be able to convince yourself that your program is actually working correctly or that it's not working correctly. And of course, similar thing is true for robotics, like if you print out, if you're implementing a controller, your controller output is going to be some floating point value that will set the speed or the torque on the motor or velocity on the motor, right? So then you print that, and then it's like 0.3, -2, -1, 0.9. Whether this is the right value or not is impossible to say. And the computations are often easy enough that there is indeed no bug in there. It's something at a higher level, the way that you generate the problem. So make sure that you know how to use the tools that are available to you in order to analyze your solutions, especially in the area of robotics, machine learning, AI in general. It's not something that the problem is that lots of code in robotics or machine learning, you have a neural network, it never core dumps or anything like that, right? You usually don't get an exception. It's just that your robot, your actuator is set to 12 degrees instead of 19 degrees, right? Which means that your robot is trying to pick up the cup here. So you know something is wrong because you cannot pick up the cup. But why that is happening, in order to debug this, is often requires some visualization. Also potentially some test cases, test runs, regression tests and things like that. Because in a robotic system, in a SLAM system, it could be anywhere. Did the vision not see the landmark? Did it see the landmark at the totally wrong place? Did it mislabel a landmark that wasn't really there. Like, was it a phantom random landmark that shows that appeared somewhere? Did the controller, the gains of the controller, were they set correctly? Did the calculation send the correct? I mean, 0.9, it's a real-time domain as well, right? So as the robot is driving, 0.9 may be the correct value 1 second before, but now your robot already moved. So all of these dependencies are not easy to debug, not easy to figure out. That's why being able to generate these kind of plots quickly and being able to analyze them, the data that you actually have, to get a better understanding of the data that you have, is crucially important nowadays. Okay, good. Then that's it for today's class. I actually wanted to talk about Gaussian normal distribution as well, but we'll do that next week, next month. Okay, and soon. Do you have a memory stick? Because I have. That? Or maybe. Bye. Bye. Okay, good.
反正它都放在那个下午再来拿也可以。
那下午会你有什么打算？
我会来收尾。